Okay, friends.
All right, fantastic. Our next speaker is Pieter Abbeel. And Pieter, without further ado, I'll let you take it away.
All right, can everybody see my presentation?
Can you make it full screen?
Let's see, how about now? Maybe let me get rid of the black border.
No, we're seeing the editable version of your slides.
Seeing the editable version of my slides. Interesting.
The desktop.
Oh, got it. Okay, let me stop share for a moment.
Maybe try sharing your desktop instead of the application. That might work better.
Yeah, as a downside, I can't see anything else that's going on. So that's why I was trying to do it this way. But let me try one more time this way to see if it can work directly this way. How about now?
That is better.
Can you see the full slide?
Yes, thank you.
Okay, great. Well, Li Hong and Mark, thanks so much for inviting me, and very excited to be here. Already learned many things this morning. Thank you to Navina and blanking on the name who came before me, Mathieu. And looking forward to our panel later. I want to focus on one very specific work that we've been doing recently on weighted Bellman losses for improved signal-to-noise in queue updates. And this is work together with Keeman Lee, Misha Laskin, who are both postdocs at Berkeley, and Arvind Srinivas, who's a PhD student at Berkeley. So often when running Q-learning, what happens is you might encounter some instability. So if you run Q-learning naively, you update your Q function with a target value, and that would be reward plus discount factor times max over actions of Q value at the next state. But if that next state, st+1, is not been seen yet or not been seen very often, and you haven't seen any related states, then it's very likely you have a high error in that target Q value, or if just some actions in that state haven't been seen, then the max over actions might result in a very high error in your target Q value. And so when you run Q-learning, this will just propagate into your Q value for state ST, action T, and then things can destabilize. Of course, people have found various tricks to deal with this, and probably the most common trick is to keep around 2 Q values. So maybe an older one, or maybe just 2 separate networks. And that's done in double DQN, which kind of introduced that as the mainstream thing to do. But then since then, it's also been adopted in TD3, SAC, and pretty much anything that uses Q functions these days will have 2 Q functions, and then compute the max to find the argmax and use the other Q function to then pass on, or possibly just pass on the minimum of the 2 Q values to stabilize. So effectively bringing the Q values down, avoiding blow up. But in the process, you're actually losing a lot of signal. So there's no reason to believe that the lower Q value is necessarily more precise. It's just more stable. And so the question we're trying to look at is, okay, yes, more stable is good, but can we also try to get more signal in the process? And we'll have to do some extra computation, but we're willing to do that here. So what if we could somehow, in our Q-learning loss, weigh the terms by some confidence score about the target value? So if we somehow could know whether a target value is likely precise or not likely precise, we could put a weighting term there, and then based on that, update our Q values or optimize our Q function loss. Now, a question then is, how do you quantify the uncertainty on a target value? Well, that's actually pretty well understood how that can be done. It's not necessarily perfect, but it can work pretty well, which is you keep around an ensemble. So let's say we have an ensemble of Q functions. We can have uncertainty estimates from that has been shown before to work pretty well in, let's say, DB exploration via bootstrap DQN, or the work by Lakshmi Hiranian et al. Also using deep ensembles to do uncertainty estimation. So imagine we have an ensemble, then we can use it to reweight. So we can look at the variance. We have an ensemble, each member of the ensemble computes a target Q value. We can look at the variance of those target Q values and then reweight. And in our investigation, initially we actually tried to reweight by 1 over the variance or 1 over the standard deviation, but we found that didn't work all that well empirically. And so we then investigated just reweighting by the sigmoid of the negative standard deviation plus 0.5. So we kind of everything gets at least some kind of weight. We can't drive the weight of anything to 0. Everything will be between 0.5 and 1 in the weighting. And empirically, that worked best for us. Now, I know it's a workshop for theory of reinforcement learning, so a lot of opportunity for more theory here. This is just a purely empirical observation that using the sigmoid on the negative standard deviation and then bumping it out by 0.5 to not discard anything, even if we're very uncertain, very high standard deviation, we don't want to discard it. It was still included in our updates. And so then we have a weighted Bellman backup loss as a consequence with these sigmoid weightings. Now, once we have an ensemble, might as well use it for other things. So another way to use an ensemble is to use it for exploration. If you doing action selection for taking the actions, not for your Q updates, but for taking your actions, you could look at the standard deviation and use it as a bonus to favor actions that you have more uncertainty about than ones that you already know a lot about. So in what I'll present in the experimental results, it'll be a combination of both the weighted Bellman losses and UCB exploration applied by having the variance from the ensemble. One thing that's worth highlighting here is that when we use, so let's take a look at the algorithm actually and step through it there. When we use UCB exploration, we use optimistic, we'll use the variance in an optimistic way, but that doesn't propagate directly into any Q updates. When we put together the Q learning loss, we use the weighting that I described, and we use an ensemble where each ensemble is learned completely separately. So one natural thing you might want to do with an ensemble is to average and say, hey, the average of the ensemble will actually give me a more precise estimate of the target Q value than any single one of them. The reason we did not do that, and maybe there's a way to do it, but the reason we did not do it is because once you start passing on the average, your ensemble becomes coupled. Everything starts learning together, and it's not clear that you would still get good variance estimates. So to keep things separate, we pass on individual Q functions values from each ensemble member is being trained separately. The only coupling is that the variance is computed by looking at all of them. Okay, so we have UCB exploration, and then we have these weighted Bellman backups, but otherwise it's just like regular Q learning. We looked at a few different environments, OpenAI Gym, which is an environment where we work based on state, DeepMind Control Suite, which has very similar environments, but there we use the pixel inputs rather than state input. And then Atari with also visual inputs. And in Atari, there's discrete action. The other two have continuous action. So on OpenAI Gym, we looked at 4 of the most standard environments, Cheetah, Walker, and Hopper, and Ant. We compared with some model-based RL methods, as they tend to be quite sample efficient, PETS, Poplin, MET-RPO, and also looked at TD3, which in some sense is the most direct comparison, and SAC. TD3 uses the min of the Q functions, SAC uses this kind of swap max thing, I believe. So what we see is that Sunrise, which applies UCB exploration and weighted Bellman backups, consistently outperforms SAC, which it's directly based upon. So we see a direct benefit of these two changes across all domains. Model-based RL, Poplin still outperforming in one of the environments. That's kind of an orthogonal choice. So then what happened is we looked at humanoid, where training actually takes a lot longer. So in our initial experiments, we ignored humanoid, but then we were encouraged to take a look at humanoid, train longer. All the previous experiments are for 200,000 steps. Look at humanoid at 200,000 steps, that's right over here. Nothing has really happened yet, either for SAC or for sunrise, which we call our approach. But it turns out if you run it for longer, all of a sudden you start seeing a pretty big separation between the two environments. So here we ran it for 800,000 steps instead of 200,000. And so it seems like the longer you train, you can continue to accrue more benefits. We then looked at the mind control suite, which has pixel inputs rather than state input. So here we build upon RAD. RAD is soft actor critic with extensive data augmentation during the training. Dr. Q is actually very similar to RAD, but we happen to have a RAD implementation. And so we build it on top of that. And so the first thing to see here is that once we add the two components, UCB and weighted Bellman backups, we see we have consistent outperforming of RAD, or in the very last line here, equally good, everything else outperforming RAD, which means we have consistent benefit from this. It's not literally always state of the art. Dr. Q has a few environments where it's a little better than RAD, and we don't beat it with sunrise, but the direct comparison to RAD is consistently improving it. Then looking at Atari, here we build on Rainbow, which is a state-of-the-art model-free method and uses Q-learning. So it's a direct fit with what we're looking at here. And we see that we get fairly consistent that sunrise outperforms Rainbow. So adding the UCB exploration and the weighted Bellman backups is consistently better than not having them. Overall on Atari, we see that model-based RL here, simple, actually still does best about half of the games. Also want to point out that this is at 100,000 interactions. So this is really looking at how fast do you pick up the learning in Atari. There are many other benchmarks in Atari where you look at 50 million or 200 million interactions, which is also interesting, but here we're focused on how fast can you start learning. So state-of-the-art in half of the environments. Then we did a bit of an ablation because there are effectively three components at play here. There is the UCB exploration part, there is the weighted Bellman backups, and there's the fact that we're doing a bootstrap, which you can just do on its own as done in the original bootstrap paper, which was shown to maybe also help a bit with exploration. To that, we looked at a noisy reward setting from the Discord paper. The idea here is that if you want to really investigate how much benefit you get from the weighted Bellman backups and dig deeper into it, it's convenient to introduce additional noise in the reward signal, because that's the kind of thing that you don't want to propagate, and you want to make sure that you see you're able to avoid propagating it too much. And so the Discord paper is actually specifically looking at that, at this setting where there is potential propagation of noise in the reward, and that's the orange curve. And then what we see here is that the approach we followed, Sunrise, actually is better at extracting signal over noise than what they did there, where they weighted their Bellman backups also, just like we're doing here. There's a weighting, but they weighted based on some estimated cumulative Bellman errors rather than using an ensemble. So using an ensemble seems more robust, at least in these evaluations, than the weighted Bellman backup cumulative estimates they had, which is closer to prioritized experience replay type measurements of error. So a couple of takeaways to wrap up here. It seems ensembles can be used to prevent error propagation in Q-learning, not just to prevent error propagation, but also to extract more signal than you would get from just using the min or swapping the max and the arc max, as is commonly done. Some future directions, more investigations of this in offline RL, which I know was topic yesterday or the day before. I think it could help there too, because a lot of the challenges there are about whether you're getting signal or noise as you're doing updates. It could help in imitation learning, which is very related to offline RL, because you get a lot of expert data and you can decide One of the big challenges in imitation learning is that you would go off the expert's path and would not know what to do there and overfit to things off the expert's path. This can be avoided here, maybe. And then the question is how to extend to on-policy learning. I'll give a little bit about that. We've done a bunch of experiments to extend it to on-policy learning, and we have not found so far any substantial benefits yet compared to what we're seeing here. Our intuition there is that with on-policy learning, you get more automatic corrections. You don't get that error propagation happening the way you get in off-policy learning. Because in on-policy learning, you're evaluating the current policy, so you're not really trying to go off the beaten path and not pulling in values that you don't know much about. And so the benefit might not really exist there. And then we have a preprint and archive, and the code is available. Thank you.
Thank you, Peter. This is great. We have about 10 to 12 minutes for questions. I'll let the panelists start.
Peter, great talk. I thought that was really interesting, particularly given the importance of uncertainty calibration. One question I had was, you're using ensembles to quantify the uncertainty, but my understanding is that the ensembles are good at sort of quantifying statistical uncertainty due to finite amounts of data. But if we have model misspecification, they're not going to be able to handle sort of bias in the function approximations that we're using. Do you think that's a problem in these cases, or do you feel like for most of the types of benchmarks we look at, deep neural networks are sufficiently expressive that sort of bias is not a concern?
That's a very good question. It'd be good for us to think about how to tease that apart in these experiments. We definitely haven't explicitly tried to tease that apart, and it seems like we could. As you said, if let's say we just use smaller networks, at some point we might start hitting the limits of what they can represent. I mean, as you know, even though it's a workshop for theory of deep RL, in my lab, we tend to be more focused on pragmatics than theory on average. And so we kind of just make the networks larger until we don't run into that problem, it seems. But I do think it's a very valid question, and especially in maybe domains where you can introduce a lot more prior knowledge in the structure of what you learn, and you want to introduce that, but then you might have a little bit of a bias that's introduced, and how to deal with that. I think it's a really good question, and I don't have a full answer at this point if it would be able to deal with that. Yeah.
Peter, thanks for the great talk. This is really impressive result. So I just have a very naive question. It seems that when you downweigh the samples with high uncertainty, it seems there might be another interpretation from using the principle of pessimism when you learn from finite data. I know these two are different, but do you think there might be a connection to that line of work where the updates are downweighted or using more conservative updates as opposed to downweighting on certain samples?
Yeah, it's interesting you bring that up, because one of the things, well, first of all, yes, there's a strong connection. But one of the things we notice is that if you run weighted Bellman backups without the UCB, the benefits are a lot more limited. And we've been thinking a bit about why that would be. And part of why would be is our thing has been, well, you're less off policy because you explore less. Without UCB, if you just do some Boltzmann exploration, Boltzmann exploration is effectively on policy. It's turning Q-learning pretty much into, soft actor critics. So you stay on policy, that's one thing. But I think there might be an additional effect there, which is what you're alluding to, Li-Hong, which is it becomes pessimistic a little bit, possibly, or at least it's definitely not optimistic, and you're actually taking away some exploration possibilities by doing this, and that maybe you do explicitly need to combine the weighted backups with UCB or some other more explicit exploration mechanism to avoid these issues. And then on the flip side, if you're in a setting where you want to be conservative, I think yes, it will help you be conservative.
I have a question. You weight the all term in the optimization problem. but in your initial motivation, it was to not bootstrap terms that you cannot believe. So why not just weighting gamma by omega? Have you tried it? So that you can at least backpropagate the reward.
Oh, that's an interesting question. Yeah.
I feel like
yeah,
that wouldn't.
I'm not sure how to do that. Looking at this equation, but there might be a way, because the target Q value has reward plus the noisy estimate of the Q value, and they get combined.
So the idea would be to replace gamma by gamma times omega of SA.
I see. You're saying downweight. So, yeah, I think if you want to be conservative, if the goal is to be conservative and stabilize, I could see that being effective. It's less clear what it does, aside from stabilizing, because you're cutting out one of the two terms, which is,
Isn't that going to change the problem, because essentially you've changed your gamma for that state? If I understand the suggestion.
Yes, you will change gamma for the state, but depending on the certainty you have on the Q value that you want to bootstrap. So at least if you're uncertain about the Q value, you can bootstrap the reward, or you can look at the smaller reason, and that's what makes the Q value. If you put gamma to 0, everything is easy. And I'm a bit exaggerating, but it's easier with smaller gamma. So because here you somehow lose part of the information by putting you lose part of the reward information locally. Yeah, it was just an idea. One thing's good.
well, I think there might be something that can be done. I'm not sure the exact format we're discussing right now will work, but I do agree that there's a big difference. The reward often is certain, you know exactly what it is, and the future state Q value has a lot of uncertainty, and treating them specifically and to account for that, yeah, I think it could be interesting. And this is definitely not doing that.
Thank you.
I have some questions or two related comments. I mean, very interesting idea. So one is basically by changing W, you are effectively changing the problem that is being solved, like the underlying distribution of the data would be changed. So I guess one question is that why this choice? And kind of related question is that what is the optimal W? Like if you have all the information in the board, how do we want to choose that W that implement what we actually want to get out of it, like reducing the error propagation or something like that?
Yeah, at the one-step level, I think it's maybe not too hard to think about, because at the one-step level, I think we can see this as, I mean, a simpler version would be running linear regression, where we have uncertainty estimates on the target values, and you would reweight them. You would probably not reweight them by a sigmoid. I mean, you would probably reweight them by the things we tried initially, which is one over the variance or 1 over standard deviation, however the math works out, to have kind of, if you assume some kind of Gaussian prior and uncertainties, and you could do it exactly that way. What's different here? Well, one, the Gaussian assumption might be wrong, so that might be why that weighting didn't work well. And there's the propagation effect that you alluded to, Amir, that also makes it more complex to think through what the perfect thing is to do. I think, yeah, I'd be very curious if somebody can figure out what is the, theoretically correct way to do this. I'm definitely not gonna, claim that this is guaranteed to be the thing that comes out of that. But hopefully it's somewhat close.
Okay, thank you.
Also saw a question in the Q&A about the footprint of this. So that's a really good question. So we found that using 5 neural networks for the ensemble is enough to pretty much have all the benefits, at least in the environments that we worked in. So yes, the footprint does become 5 networks rather than 1. In practice, you don't have to have 5 completely disjoint networks. You can also have networks with shared core and then separate heads to save some memory footprint. And people often already use 2. So it's going from 2 to 5 really, rather than from 1 to 5. But yeah, there's definitely an additional memory footprint there. And computation footprint for that matter, because for every update, you're going to do 5 times the computation effectively compared to normally 1 time.
Can I ask a question?
Sure.
There's sort of this discussion going along in the chat. So maybe this has been answered and I missed it because I was looking at the chat, but there's a question about how this affects the weighting on the states and that, state weighting matters for function approximation. So do you have an idea of where this weight converges to, like where WSA goes to? I mean, I know it's changing as time passes. And then, where might it go to? Is it going to become uniform eventually because you're equally confident about everything, or what's going to happen?
I can make a guess, but we have not looked at it. I mean, the educated guess I would make would be that as it converges, the Q values become the same across all the members of the ensemble. And so the weighting would go to 1. But yeah, we should probably check.
Great, that makes sense.
All right, we're almost out of time, but actually I'm going to be quite selfish as a moderator. And I think, Peter, I could spend a whole afternoon picking your brain about this. So I have a question for you, a very practical question. There's an alternate way to implement the weighting as you've done here, which is to use the weights as priorities. And you've sort of alluded to this, right? You could do prioritize replay and just then weigh everything by 1. Have you looked into this? What's your feeling that one should work better than the other?
And if your samples, if you do enough of it, I think you're right, Mark. It would effectively be the same, because you would just do more updates that are all weighted by 1, but more updates for certain terms than for others. It's interesting because people don't really do prioritized experience replay this way. So essentially, maybe the way I would practically interpret it is, hey, maybe there's an opportunity to experiment with prioritized experience replay using this as the signal and see what happens.
That's right. The reason I'm asking is because I'm thinking this is something actually we've looked at, and it seems like if your weight, not the version you're presenting here today, but if your weights are very small, then effectively it's a wasted gradient update, which you would rather reallocate to train on a different sample. Right. Now, in your case, you're capping them at 0.5. Maybe no samples are wasted, and maybe that's why that wouldn't make a difference. But
yeah, I mean, we experiment with not capping at 0.5 and letting it go to 0, and that didn't work so well. Just as an additional bit of information.
I know prioritized replays actually can be quite finicky because it introduces additional variance in the process. Maybe that's a reason to weigh them instead of sampling.
Yeah, I'm very curious now. Let's see if that might work.
Sounds good. On this note, if there is a quick question, we could take a question. Otherwise, we can also thank the speakers. Any other questions before we wrap up? All good. Then thank you again, Peter. Thank you all the speakers this morning. The next step is for us to have a coffee break and recover from Zoom fatigue. After which we'll have one more talk after the break, and followed by a discussion. I always get my time zones wrong, but it is in an hour. The discussion is the coffee break lasts half an hour, and the discussion is an hour from now. So thank you very much all, and see you in half an hour. We will start at 2 p.m. sharp Eastern time. Thank you.